Okay, so this is about the fundamental theorem of calculus. It consists of two parts. Just an overview so that before you head out to the questions, you can keep these two things in mind and being able to differentiate how come there's two parts to this. So basically the first part, interval notations are very small and tiny, like with the subscripts and the interval a to b and all of the notations. So it's kind of hard to catch what's needed there and how to differentiate between different types. So part one basically says any function g at x is integration a to x, and it's f. Because x is already taken, you write the letter, any letter that works. You can say s, any alphabet, 25 letters. I think there's 26 letters in the alphabet, excluding x, and probably excluding a too. Common notation will be just t, so ft and then dt. So basically what this means is, notice that this is a function expression. This is not a number. For the definite integrals, it was going from two set numbers, meaning it is over a certain interval. But this time, x is a variable. It can vary. See how these two are same. It's the same variable. Because it's a variable, definition of variable means it can move anywhere from, say, typically a set domain is always denoted in integral as going from a to b. So a is already showing up here. So x is going to lie somewhere between the two. X is going to fall somewhere between these two. It can be considered as area so far. It's like area thus far. So if we are to draw a diagram, it's going to be like, say the fixed window frame is for the interval is a to b, and choose some arbitrary value called x. And notice this is x-axis. So x can move freely anywhere from between the two. It can stay at a or it can go all the way to b. So you can always move. So it's a variable. It's varying. This ends up becoming a function that contains the variable x. Part two. So basically this is saying that derivative of g at x is equal to f at x. That's what it's saying. So it's like these two are related in the way that this is differentiated version of this, and this is the antiderivative version of that. That's what this is saying. Part two is a very practical application, and this is why this whole concept of fundamental theorem of calculus is considered to be like one of the greatest inventions of all time for human achievement. It's because it has made a lot of calculations that were so hard to do in the past, and they have made it so easy. Part two builds on part one. So what it's saying is this is now based on two specific numbers. F at x, d at x is basically f. This is capital letter F means it's antiderivative of this. And so of b minus f a. I was getting one step ahead. There's the constant. When we take antiderivative, there's the constant of c that gets added up. But in the process of subtracting the two, the c gets cancelled out. We can just choose a simple function without the constant factor. For that reason, we don't have to have anything to do with c at this point. F, say variable x, just general case. When we take the derivative, that's equal to f at x. This is the same thing as this. G at x is the same thing as this. But that's the notation that they use typically in all the textbooks and all the representations in calculus. So we're going by that. This means is once we have found the expression for g at x, then we can simply plug in these two endpoints, which means when we find the area thus far, we can just subtract off area to the point A. So the area between going from interval a to b under the curve that's associated with this, which is antiderivative of this, is b minus a. So key things to note is that this goes from a to b, and this goes from a to x. This ends up becoming a function, and this ends up becoming a number value. Keeping these two things in mind, that they're all built upon fundamental theorem of calculus, then we can head to the questions.